Right, well, thank you to the organizers for inviting me to give a talk, and thanks for Nelson to set up the scene. Although my theory is, the theory I'm just going to describe is slightly simpler, and I don't think I suffer from Twitter science. This model is really just couple dark matter disformally and conformally to a scalar field. So these models are very simple compared to what Nelson was talking. So there's only one species coupled, and it's a species we don't know much about. Oh, I should say that the work is done in collaboration with Jürgen Mifsud in particular, and Jack Morris. Jürgen is also going to apply for postdoc positions. I can only hardly recommend him. He's a really good student. So if you have any postdoc positions, please keep an eye on him. He's excellent. Okay, so the theory I'm going to discuss is a scalar tensor theory. Let me just find, where is the light? Is that this one? Perfect, great. So we have a normal scalar tensor theory in the sense that there is a species non-trivially coupled to a scalar field, but the standard model particles are not. Okay, so we have just a standard theory. Dark matter is coupled to the scalar field via this metric G tilde, where G tilde, like in Nelson's talk, contains a conformal part and a disformal part. So now to your question, how to define the energy momentum tensors, here's a definition. So you take this action and you just do the variation with G, but this formally coupled species has a G tilde, and this Lagrangian depends on G tilde as well.
So
and
scalar field will be inside there, right?
it will be in here.
Why not the opposite? I mean, so this is the definition, right?
Because if you do this, you derive in the standard way, the standard form of Einstein's equation. It's just the definition of these tensors which are in Einstein's field equation. I suppose you can do it differently, but why? Yes.
So this is an arbitrary split, right?
I would say it's a natural split.
These interacting models, they cannot come from gradually. I mean, the total energy momentum tensor is conserved.
Yes. Yes. Yes.
Now, the way to split that in different sectors, it's okay.
But yes, I think you can do this, but I don't think that will change anything. But Nelson has defined the energy momentum tensor in the same way. Okay. Yes, so we have done it, as we just said, just to obtain the standard Einstein's equation and energy momentum tensor for the scalar field, for standard model particles, and for dark matter. As Nelson has said already, also in this theory, the scalar field is driven by potential, but also by this coupling function Q. And dark matter is no longer conserved because of the coupling in a standard way. As you have seen it before, you have this coupling function here and the derivative of phi. Now with a disformal term, the function Q is much more complicated, and I think this version of the coupling function was written down by Miguel in a paper with Tommy Koivisto and David Motta. So you see here the trace of the energy momentum tensor coupled to the conformal term. That's a standard thing we have seen many times. And the disformal term contains these derivative interactions here. Okay, so these two terms here are the new ingredients. Now this theory contains a standard coupled quintessence, which has been discussed for years now, where you have no disformal term, but you have a conformal coupling in this form. This was written down first in a paper by Christoph Wetterich in 1995, and then Luca worked out the cosmology in 1999. So here in these theories, dark matter interact with the scalar field, and as a result, you have an additional force. And the coupling strength, or the charge as they call it, is given by this conformal term beta here. So you have an enhancement of the Newton's constant 1 plus 2 beta squared. Now, if I would make this theory more complicated, so two meta species, I would have beta 1 and beta 2. I've got a 2 beta 1, beta 2 as a force between two different species. And if one of the betas is negative, you can actually reduce G effective. But otherwise, as Lavina said, I mean, it's very hard to do in the scalar tensor theory, but I need to talk to Filippo about, because you mentioned this is possible via some ghost. I need to talk to you about this. I didn't get this. But anyway, in these theories, you have always an enhancement of Newton's constant. But yeah, sure. But I thought you have it in the scalar tensor theory that you get a reduction of G effective. I thought that was the case. If that's the case, I would like to know how this works. Anyway, many people worked out the constraints of this theory. Valeria, a recent paper by Mark Trodden and collaborators in July, and myself with Jürgen just in September, we find that beta roughly is less than 5 times 10 to the minus 2. Okay? So it's really small. And for me, well, the attractiveness is really getting lost here, but with beta being so small. Although Philip pointed out to me, we should be actually celebrating this because we are actually testing a force which is very much weaker than gravity, and we are nearly arriving at constraints which is similar to what we have for baryons in the solar system. So maybe we should celebrate this. But from the theoretical point of view, okay, I don't know. So what I call extended coupled quintessence is just adding now a disformal term. And then FLRW, I should not forget Lemaitre, although he was Belgian anyway. I add them, and you see, you have this in this Robertson, Walker, Lemaitre, Friedman, now mix up the names. You have this form. What appears here is the Hubble constant, the derivative of the potential, and rho c, also on the bottom here. And in general, this becomes time dependent. You could choose c of exponential form and d to be constant. Q will evolve in time. And that will have some important properties. I will come about this later. So for most of my talk, I will assume an exponential potential, a conformal coupling, a constant disformal term, because it sets actually a mass scale. So d is not unitless. It has it's 1 over mass to the 4. And just set a mass scale. That's just simplicity, because I didn't think it had anything new, but Jürgen was quite meticulous. He said, no, let's just do it properly. So later on, we switch on also time-varying or field-varying d. But for now, it's just a constant mass term, which adds. So why I became interested in this? Well, there was first this paper by Miguel, and secondly, as Tommy Koivisto and Willis and Zavala pointed out, this can actually be motivated in string theory, and I quite like the motivation. So this is not a brain world theory, but it contains higher dimensions, and these higher dimensions are curled up, and there is, according to string theory, there could be a warped throat, so an ADS space, and you have a D3 brain moving along this warped throat, and if there is some stuff sitting on this brain, it contributes to the Hubble expansion, and it could be dark matter. So the disformal term comes simply from the fact that the induced metric on the brain, which you have to plug in to obtain the effective field theory in 4D, contains a disformal term here. H is just the warp factor of this throat. And as you can see, H, so the conformal factor, or H to the minus half, and the disformal factor are actually related in these theories. Now, I will make it a bit simpler. I use exponential functions, but this should be actually worked out. It's just a bit harder to do also numerically, because these H's are inverse. Well, it's phi to the 4. So it's a bit harder to work out, but we will do this in future. But this is a very nice motivation for the type of theories I discuss. So, okay, so the equations of motion, there's not much to say, really. Standard Friedman equation here in conformal time. Radiation and baryons are standard. Dark matter and the field phi interact via this field Q. Okay? Now, what I'm going to do, because I need it later, if you compare these theories to supernova, we usually assume that dark matter scales like 8 to the minus 3. It's not the case here. So the part which doesn't scale like 8 to the minus 3, I put it into dark energy. Okay? So rho dark energy effective is just the scalar field dark energy plus dark matter minus the contribution which scales like 8 to the minus 3. If rho c would scale like 8 to the minus 3, this contribution would go away. It's just rho phi. But if it doesn't scale like 8 to the minus 3, this part is in dark energy, absorbed in dark energy. And the effective equation of state is then defined via this equation here. And then you just, couple equations together. And you find the effective equation of state is given by the pressure of the scalar field divided by rho dark energy effective. Okay?
So as I remember, Planck would provide a bound that the dark matter scales as a minus 3 with a precision like something like 10 minus 3 or 10 minus 5 with this factor 3. So it's...
Okay, great. Yeah. Okay. Mm-hmm.
It's a very strong constraint.
That's excellent. Yeah, good. Yes. But at the moment, is it already the constraints are like this? Because this is not constant. I mean, this part here, how much actually goes into the scalar field it's not constant. So I don't know whether Planck assumes it's a constant part which is there.
This assumes this lambda plus dark matter.
Okay. That's just redshift dependent, because that's slightly more complicated here. Mm-hmm. Yeah, because this depends on time. Okay, so what does the effective equation of state do? Well, the red one is just the scalar field equation of state, p phi over rho phi, and this is the effective one. And as you can see, and this is already well known, a paper by Justin Curry and Pier Stefano Corsaniti, that actually it looks like phantom to us, these interacting dark energy models. And this is just a conformal case with alpha quite small, which is actually okay with the bounds. And you can see, even for these small couplings, you have an equation of state which can go below -1. Although here, in this case, at higher redshift. For the disformal case, this is purely disformal. No, this is a mixed case, conformal and disformal. So we have still alpha is 0.02, and we switch on a disformal term of the order of milli-electron volt, same scale as Nelson mentioned in this talk, and you can see that has an even bigger effect, okay, because you just add another contribution to the effective equation of state. So it looks more phantom in these models. What does the effective coupling do? Well, I define now a beta effective as minus q over rho c. In the conformal case, it will be just alpha. With the disformal contribution, this thing becomes, as I mentioned, time dependent. So, okay, you can't see this. I even can't see this. Okay, so it's a conformal case, and let's just read. The black one is, lambda is 1.15 in all the plots. The first black plot, the black curve, is just this one here, just a constant conformal term. Okay, and alpha is 0.14. Interesting story. Jack came in and said, Carsten, what alpha should I choose? And I was very busy. I said, pi. And he said, oh, that's too big. And so he went to his office and just cut the 3 off and did 0.14 because he just didn't know what he should plot in. So that's 0.14 came in like this because this is a crazy number. The disformal term here, the blue line, contains no conformal coupling, but the dm is of order 0.43 milli-electron volt to the -4. Okay, and then you have a mixed term where we switch on alpha 0.14, and you see this is the red line, and then the magenta line is just one where we slightly change dm. Okay, right. What does the effective Newton's constant? So this is the effective Newton's constant between two dark matter particles, which is related to the beta effective via this equation. And you can see initially, this is, well, I should actually point this out. Sorry. Initially, the coupling is 0, effective coupling, and it switches on at the redshift, I don't know, 10-ish, depending on the parameter 10. It becomes bigger. And it goes out all the way up to 0.5. Now, the effective Newton's constant between the particles becomes, at late redshift, per order 1.5. So it is enhanced by 50%, depending on the parameter of that theory. Okay? Right. So what about perturbations? Well, you have seen this. So the Newtonian gauge, not much to say here. Well, yes, I should say. Okay, so what changes really is the equation for the scalar field and for dark matter. There are two terms which are of importance, delta Q here and this Q. Now this delta Q, if you have a conformal coupling, disformal coupling, it becomes K dependent in this term B5. So the delta Q is quite complicated, but I think, well, it just contains background quantities. But important bit is it becomes K dependent. Initially I thought, okay, that's only possible of interest for nonlinear scales, but actually what Jürgen found is that it's actually more, it could also have an impact on linear scales. I'll come to this in a second. So if you do the quasi-static approximation and you find that delta Q at late times approaches Q, which is the background value times the density contrast of cold dark matter. Okay, that was actually pointed out in your paper, Miguel. But what we've checked with Jack is actually when things happen. So here, this green line is Q delta Cm. That's what it approaches to. And this is the exact delta Q. And you can see for K is 0.3 megaparsecs, it deviates quite a bit, and later it oscillates around and then it settles to this value here. If you change K, things happen at a later time. Okay? And you see these oscillations, and you see the K dependence here. And this became quite important for what I have to say later about the growth rate. Now, it is well known, and Valeria worked on this for many times, many years, the conformal factor will just screw up your CLs. I mean, here for alpha is 0.2, you can see there's quite a deviation from a typical lambda CDM model, first of all, the peaks are moving and also the amplitude moving. And also the power spectrum changes. With a disformal term, this is purely disformal. So Q here actually, at late times, is quite large, the effective coupling. But you see, it doesn't affect the CMB and just tiny bit the matter power spectrum. That was initially bad news, we thought, because that means that you can't really use the CLs to test these disformal couplings to dark matter. And here's a mixed case, and I think that's one of the, if you take one thing home, this is the one. This is a plot for alpha's 0.2, and we have seen the CLs. It was not very good. But if you switch on a disformal coupling, the CLs are actually going back to the uncoupled case, which is a blue line here. So a disformal term helps shielding, so to speak, the conformal contribution. And we wanted to understand this, and we did calculate the CMB separation because that's the thing we can do. So there's an approximation for the delta L, for the peak separation, which is given by this formula here. That's an old paper by Wayne Hu. So you need the conformal time now and the last scattering, and you have the sound speed, which is the baryon photon plasma, which is a standard value, and tau LS. So we found some approximation for tau LS, which are actually very good. They are given in terms of what is called the average dark energy effective. So what you do, you take your rho effective, divide by the critical density, you get your omega effective, and you average this from from 0 to tau LS, okay? And divide by tau LS. And this integral appears in these expressions, okay? There's another quantity which you calculate, which is tau naught. And this depends on the effective or the averaged effective dark energy equation state. And to do it is to weight this by omega the E effective. So this we needed to do, okay? And then we found tau can be written in this form here. Now, we plug this in to calculate delta L, and we compare to the exact case, and we are of order percent and below with these expressions. So, okay, let me spend some time on this. Okay, so dark matter would be sitting here, okay, so about 304. There's almost no dark energy effective initially, and the equation of state would be -1. Now, take a look at the conformal case only with different lambdas. So lambda is 0.5, a rather flat potential, and there's T potential here in the red curve. And we switched on, so you are here for, let's take lambda as 0.5. You are nearly lambda CDM, but when you switch on the coupling, you can see you move along in this plane along this line here. And you see if you switch on the coupling, you end up with a peak separation, which is different, 310, 315, depending on the coupling. Okay? And if you change lambda, you can even deviate even more from the 304 for lambda CDM. Okay? In a disformal case, this becomes interesting because, as you can see, you don't deviate much from the 304 line at all. So let's take, for example, this lambda is 0.5, and you switch on a disformal term, you can see it never goes far from the 304 line. If you switch on, or if you make a lambda higher, so here's for lambda is equal to 1, you deviate more, but not that much from the term. That means, compared to the disformal case, for conformal case, the disformal term really doesn't change the peak separation much. And here's the case for the mixed term. So you have omega dark energy, the average dark energy, and equation of state. Again, 304 is somewhere here. And you don't deviate much from the 304 line in these mixed models. That's why, or that's one of the reasons why the CLs look actually quite okay in these disformal coupled models. And that is in contrast with the purely conformal coupled models. Okay, so this plot here shows, and that's based on an idea by Linder, he plots h over h naught versus the growth rate times sigma 8. And here the dots are for different redshift. So this red dot here, these circles here are redshift 2, these stars here at redshift 1, and these crosses here at redshift 0.5. So the idea of Linder is to say, okay, if we take this plot and we just follow h of z as a function of fm times sigma 8, these turning points could actually help us to distinguish between different type of modified gravity theories. Now, as you can see here, the uncoupled case is the blue line. That is roughly what lambda CDM would do-ish. Where the conformal, they deviate quite a bit. The purely conformal case deviates quite a bit. But at the turning point, actually, it comes close to a purely disformal coupled, whereas the mixed deviates quite a bit at the turning point. So if you could construct from observations a plot like this, they could help distinguishing between the conformal, uncoupled, and disformal in mixed cases. Okay, we don't have, I don't think there is a plot yet with data points as such, but it would be something interesting to do. Now, talking about the growth rate, so here, what I plot here is the growth rate defined as in Nelson delta prime over delta as a function of k for different redshifts. So this is at redshift 0.5, 0.52, 0.54, 0.56. In the conformal case, it was well known that it goes up and has a bit of a peak and then it flats out. This plot is well known, okay? But let's take a look at the disformal case and the mixed case. What you can see is, first of all, this peak is not as broad in this disformally, and also the mixed cases, and you see small oscillations. These oscillations come from the fact that the coupling oscillates around this Q delta value. Okay, that's where this is coming from. So potentially, and we need to investigate this in future more closely with the spherical collapse model, is that you can distinguish this broad feature in a conformal case from a rather narrow case in a disformal with a disformal coupling. So the hope is that this is a distinguishing feature of a disformal coupling, but it remains to be seen. Okay, so in the last 5 minutes or so, or 10, or no, 5, I think I've got 5-ish. Okay, all right, 8, perfect. I can talk about the constraints. Okay, so at this point, so we talk about the conformal coupling, but now Jürgen was insisting we should also let the disformal term evolve in time. So we introduce a beta. It's slightly different notation from Nelson's, and we have an exponential potential. For the priors, we say alpha should be between 0 and 0.48, beta between 0 and 3, because, I mean, this is something we know is 4.8 is already, in a purely conformal case, ruled out. So we thought, okay, we go up to this point. For beta, we know nothing. So the range was quite broad, from 0 to 3. And for the mass scale, in milli-electron volts, between 0 and about 1. Okay? And lambda, that is the slope of the potential from 0 to 1.7. Interestingly, if you were to expand this slightly, these ranges, we were struggling with a class. It didn't run properly. Didn't want to. As for data, we assume, well, we just take the Planck value of TT and also polarization and lensing. Bow, which is all in the packages. The only thing which is worth pointing out is we took constraints, so we took priors on the F-statue or the Hubble Space Telescope values for the Hubble parameter today. This is about 67 point something, and this is about 73 or 72 something. So quite a bit difference. We wanted to see whether this has an impact on the data analysis. And we also, there's a point here missing, added 8 data points for sigma 8, and we splitted them into 2 parts. There are 6 data points which are consistent with lambda CDM. Okay, it's perfectly okay. There are 2 data points which are, as you may know, are struggling with lambda CDM because they predicted too low sigma 8. And we just wanted to see what are these doing to the parameter constraints. Right, here we go. So, okay, this is for the conformal case. And we agree with Valeria's work. We agree with Mark Torden's work. So what do you see here? It's quite busy. So the red line, the red region is temperature only, barrier acoustic radiation, supernova, age of Z, and the F-statue value of the Hubble constant. The green is the same, but we just assume the Hubble space or Reese Hubble Space Telescope value of as a prior for the Hubble parameter today. And you can see there's a bit of an effect here. Just a CMB, okay? On the value for alpha, and also here for omega meta, sigma 8, and H naught. Okay? If you turn on the Reese value instead, this you have, well, there's a green one. You have blue, and they have these sorry, this is with EE polarization, then it helps a bit, but not much. Okay? Right, so here we go. This is the one I really had in my mind. This is now switching on large-scale structures because the constraints get much bigger. So ACA are the values for sigma 8 which are consistent with lambda CDM, and the CA are the one which are in strain with lambda CDM. I should say these CA values for sigma 8 are already they're already not in agreement with lambda CDM. Any conformally coupled model or disformally coupled model increases sigma 8. Okay.
Sorry, what are these? What are actually the probes for this sigma 8?
Okay, so one is from Rosat, 2009, the Munich group, and something else. I need to check it on my paper.
But you mean this is like counting clusters or something?
Yes, yes, yes.
Are you sure that nonlinear process is
Mm.
to do with your model?
Well, no. I mean, you mean what?
I mean, formation clusters is high nonlinear, right?
That's very true. That's very true. And that's very true. But when people compare these modified gravity, I mean, we're not the only one to compare modified gravity theories to these data. It's even worse than this, because the data, when they analyze the data, they calibrate to n-body simulation with a lambda CDM. So you have to take those with a pinch of salt, or grain of salt.
Exactly so.
Yeah, sure. But we wanted to see what happens if this really persists in these models. This is what is done many times over. I mean, this is not.
Oh,
Yeah. But yes, we have to take this. But it's very true. One has to be careful with this. I agree with this. Yes. But on the other hand, as you can see from these plots, if you so let's just compare. Let's say the gray one, okay, with the blue one, because that is the same Hubble constant today, or the prey on the Hubble constant today. So the gray one is here, and you can see if we switch on if you allow for these two data points for sigma 8, there's quite a reduction on the allowed value of alpha. But as Ignacy just said, we should be careful because it's those data analysis assume lambda CDM from the start. But quite a few modified gravity papers compared to those data sets. So that's the reason why we did split them. Yeah. But you can see, if they are true, if it really turns out that sigma 8 is so small, it does have quite a bit of an impact. I would say that whether the F-Stasio value for the Hubble parameter today or the Reese value, it has some slight effect, but it's not as drastic as I thought initially. So this is conformal only. So let's go to the disformal. And this is also a busy plot. Essentially, these regions here are CMB and background, and these are regions here are with large-scale structure values. And you can see, if we were to nail down structure formation, the constraints get much better, although it's clear that DM is hardly constrained, although lambda is. Okay. And this is here for beta 0. If we switch on beta, actually, there's this plot here. We just wanted to see, and by reducing one parameter, we said that V naught is the potential amplitude times dm is equal to 1 to reduce one parameter. Then you can see beta versus lambda. I mean, again, beta is not constrained where lambda is. Okay, so these plots for F-Stasio. So low values for H naught and high values for H naught. There's a big difference in the constraints on lambda. So from 0.75, and if you have a lower Hubble constant, it goes all the way up to 1. In these mixed models, I did tell you that a larger value of alpha seem to be allowed, and this is the plot really, which confirms this. So we plot here in these mixed models. So we have this formal coupling. V naught times dm is equal to 1. And this alpha lambda plane here, you can clearly see that it goes all the way up to 0.3. And if you allow for F-Stasio value, it even goes higher. Okay? So larger values of the conformal coupling are allowed with these disformal terms. To conclude, okay, so observations of these models are consistent with zero couplings, as we would have expected. But I believe that there are some interesting features which are worth exploring, in particular, this oscillatory behavior in the growth rate. I found it quite interesting that the disformal term allows for larger conformal coupling. So if your theory has a large conformal coupling, don't rule it out immediately. Check whether you have a disformal term somewhere. It leads to interesting features, as I said, and the nonlinear evolution needs to be studied. And the hero of the day is Claudio, who I think has done the first disformal n-body simulations. And I encourage you to really work on this further because there could be quite interesting effects. But I believe it's very hard to do. But it has to be done. Now, I mentioned that there's a motivation coming from extra dimensions. But what we have done is not actually looking at that model. That will be the next part. And one of the differences is that the scalar field is actually not a standard kinetic term. It's a dBi field. So in this case, and Nelson has actually shown the plot, the equation. The equation of state for dark matter is the one which is on the brane. I mean, in these models we assume 0, and also in the original paper by Tommy. But it could be, warm or tepid or whatever dark matter. And if the field starts to, like this, 1 minus d phi dot squared. If the field starts to evolve, say you have an equation of state, which is a third, radiation. If the field starts to evolve quickly, the pressure, as we measure it, drops to 0. This is the guy which appears in the equation in the structure formation equations. So there's a relation between the equation of state of dark matter confined on the brane and dark energy equation of state. So that could be potentially quite interesting. Yes, and of course, is there any other motivations for conformally, disformally coupled dark matter beyond the extra dimensions and branes that would be nice to explore as well? And with this I close. Thank you.
Thank you. Other questions?
So just to comment on this extra-dimensional thing. So because the scale you're choosing is actually quite a low one, you said it was milli-electron volts, right? So
oh, right, yes. But that has, okay, so if we were to larger, then it's just reduced.
Yeah, so in the real example, so that means the cutoff of the effective theory is milli-electron volts for the scalar. So in the actual brane examples, at that point you also expect to be getting extrinsic curvature corrections and so on at that scale.
I'm not quite sure because I don't have the slide here, but hang on. It's slightly different this because there is no dm times phi to the whatever. You just have a phi to the -4. So the scale is actually set by the scalar field.
There's the derivative operators that I'm counting. So these are non-renormalizable operators, the couplings.
Yes.
So they come in at a scale.
Yes.
And so that's also the scale that then you start to expect extrinsic curvature and curvature corrections in the brane effective action.
Okay.
So we say when you do dBi inflation, you check that you're in the region
that
where
assumes
these are small.
That assumes that the dm is of milli-electron volt here actually turns out to be the same number you get here, because I don't sure you can. The scale we have here for dm carries over to that model. I'd rather prefer to do the data analysis and see what would be allowed.
Yeah, I would worry about it though, I think.
Okay. Okay. Mm-hmm.
I have a couple of questions. The first one is for the CMB. Isn't the reason that in the conformal case that the peaks are so bad because you have modifications before or during recombination?
Sure, you change the omegas, that's very true.
Mm-hmm.
But that changes the amplitude as well. So here we were interested in this peak separation.
Right, but besides your analysis, isn't the real reason that this formal coupling has this
it changes
rho in the denominator?
Yes.
Okay.
Well, it does, hang on. It does change, I mean, what you're saying is it does change the omega composition, so to speak, at recombination, right? A last scattering surface. Mm-hmm. Mm-hmm. So that's the case also in the disformal term. But it's more slightly tricky here because your Q evolves in time. And to calculate omega, to say you have an omega today of matter 0.3, it doesn't carry easily over to what it happens at last scattering surface. You can calculate easy in the conformal case, which is an easy integral. But for the disformal term, because D depends on, well, the Q depends on it's complicated on phi, it's not the only effect.
Mm-hmm.
Yeah.
Okay. And the second question is these oscillations you found in the matter power spectrum in the disformal and or mixed case. Do you think there is any hope to measure that? Because that would be very. If
The
you detect
oscillations,
something-
you mean those? Hang on. No, it's not the power spectrum. This is f as a function of k. You mean
But-
those?
Well, f
Yes.
as a function of k. That's
No, I mean, okay, so do I have hope to measure these bumps here, these small ones? No. But what I do think, so yes, I mean, this itself should be visible. That should be, this we might be able to probe. And I think what we also might be able to probe is this, hopefully, we have to do the calculation to really know, is that this, this peak is rather broad and this is rather narrow. So I hope that this would be one distinguishing feature when it comes to you calculate spherical collapse model or so. But these oscillations itself, well, some people in the audience might know better than me, so I don't know. I have my doubts because they're quite small, right?
It would be very unique.
Yes, it would be very unique. It would be unique, yes. So the hope is that it actually does something.
More questions?